Hello everyone. We will be looking at the moment of a force about a point using the vector approach. Okay? Alright. Before I go with the vector approach, I want to very briefly talk about cross product of vectors. Okay, so cross product of vectors. And you'll see why I'm going to talk about this in a brief minute. But let me first define the cross product. Okay? So the basic idea is very simple. Let's say that I have two vectors A and B. Okay, so here is vector B, and then here is another vector which I'm going to call as A. So this is vector A, and then this is vector B. And let's say that the angle between these two vectors is an angle that is theta. The most important thing that I want to point out in the cross product is the following. The cross product of vector A and vector B is going to be another vector C. Okay, some vector C which is perpendicular to the plane containing A and B. Okay, so I'm going to say that the cross product of these two vectors is a vector C. So this is vector C, which is A cross B, and this vector C is perpendicular to the plane containing the vector A and the vector B. Okay, so vector C, I'm going to write this down. So C is A cross B, where vector C is perpendicular to the plane containing A and B. Okay, and how do I get the direction of this vector C? It's by the right hand rule. Okay, so the direction of vector C is by the right hand rule. Okay, and typically what is the right hand rule is that you align the fingers of your right hand along the vector A. Okay, so align the right hand along the vector A. Okay, and then your palm faces the vector B. And then you curl your fingers. The direction of the thumb gives you the direction of vector C. Okay, is the direction of vector C, which means that A cross B is not the same as B cross A. Okay, so something that you want to see is A cross B is not equal to B cross A, and in fact they are the opposite direction. Okay, actually A cross B is equal to minus B cross A. Okay, so if I take B cross A, then it's going to give me a vector that is in the direction opposite to the vector C. Okay, so this is probably going to be some other vector D, which is going to be B cross A. So the most important thing here is the following statement. Okay, the vector C, if I take the cross product of two vectors, is perpendicular to the plane containing the vectors A and B. Okay, why is this important? Now I go back to the idea of moments. Okay, so we go back to our idea of moments. So moment of a vector about a point using the vector approach, moment of a force using the vector approach. Okay, and you will see that in order to compute moments, we use the cross product. Okay, so we shall use the idea of of cross product of vectors. Why? And for this, I'm going to bring back a figure from the previous time we looked at the moments using the scalar approach. Okay, so this is from before. Okay, if you recall this particular figure, which had a lot of things written on it. Okay, so in this particular figure, I had this beam which I had drawn here, right? So this was that particular beam. And on this beam, there was a force F1 that was acting at the point A. Point A is the point of application. Point O is the point of interest, okay, where the beam is pinned about a certain support. And then I have the X, Y, and Z axes. Then what we found out was that the moment of this force about the point O is about the x-axis here, okay? And we found this using the scalar approach. Okay, we said that first of all, magnitude is the magnitude of the force times the perpendicular distance. The direction is given by the right hand rule. Okay, so I can say that moment of the vector force F1 about the point O written as a vector is its magnitude times the unit vector I. So the thing to note here is that the direction of the moment vector is also perpendicular to the plane containing the force and the distance. You see, the plane containing the force is in the z direction, the distance is in the y direction, the direction of the moment is along the x-axis. So the direction of the moment vector is perpendicular to the plane containing, okay, this is perpendicular to the plane containing the force and the perpendicular distance. Okay, this statement is suspiciously similar to what we wrote for the definition of the cross product of two vectors. Okay, perpendicular to the plane containing the force and the distance. Okay, so the force, so that's one, and then here is the distance, which is the other. Both of them can be written as vectors. Force is a vector, distance, if I write it as a vector, becomes a position vector, which means that the moment can be given as the cross product of the force and the position vectors. Okay, so this is very similar to the idea of cross products, right? Because in the idea of cross products, we said that the vector C is perpendicular to the plane containing the vectors A and B. Likewise, we are saying that the moment vector is perpendicular to the plane containing the force and the distance. So we can use the idea of cross products. Okay, so hence we can use cross products to obtain moment of a force about a point. Okay, so this is the basic idea, and so we're going to define a couple of things. Okay, so the vector approach is the following. The moment of a force about a point is given by the following. Moment of a force about a point of interest is given by the cross product of the position vector from point of interest to any point on line of action of the force and the force vector. Okay, I'm going to put a couple of brackets here. Okay, so the important thing is the moment of a force is given by the cross product of what? Of the position vector. Okay, we said that, okay, the moment vector is perpendicular to the plane containing the distance and the force. So distance, if you write it as a vector, is the position vector. Force, if you write it as a vector, is the force vector. But then two key things that I'm going to underline in a different color. The position vector is from the point of interest to any point on the line of action of the force. This is extremely important and extremely powerful. Okay, this is any point on the line of action of the force. Why is that? Okay, any point on the line of action of the force. Okay, so I want to just maybe reiterate a couple of things. Okay, so if I want to calculate moment about a point, okay, due to a force F, okay, this is going to be given by R cross with the force vector F. It is always R cross F. Okay, so this important thing is always R cross F and never F cross R. Okay, the reason for this I'm going to post in my elaborate notes. Okay, the reason for this posted in my elaborate notes. Okay, so please consult that. The other thing is that this R vector, which is the position vector, is from the point of interest to any point on the line of action of the force. Okay, important things here is that it is always R cross F. Okay, please notice that it's always R cross F and it is never F cross R according to how we are defining things. Okay, and the reason for this will be posted in my elaborate lecture notes, because this will take a little bit of time to explain on here, but it is fairly a straightforward explanation. There is nothing much to derive here. And then the position vector is from the point of interest to any point on the line of action of the force. That is also a pretty powerful thing. Okay, to any point, right? Because now we have a choice of maybe probably millions of points to any point on the line of action of the force. And that's the thing that I want to show as to why that is the case. Okay, so to show why, to see point B, we shall consider a hypothetical example. Okay, all right, so in this particular hypothetical example, I'm going to set up first of all a Cartesian coordinate frame. Okay, so let's call this as the x-axis, y-axis, and the z-axis. And I probably have to scoot this figure up a little bit. Okay, so let's say this is the xy, and then here is the z direction. Okay, so that's x, that's y, and then that's z. And then let's say that I have some kind of an arbitrary rigid body. Okay, so this is some rigid body that is attached at the point O, and it is directed this way. Okay, so this is some random rigid body. Just shading it in this particular color. Okay, then I'm saying, okay, the point of interest for me is the point O. Okay, so point O is the point of interest. And let me say that there is a force acting on this body. Okay, let's say that that force is acting in the direction that is shown, and I'm going to write this as a force vector. Okay, so this is the force vector acts on the body. Now I'm going to take this force vector and extend its line. Okay, so that becomes the line of action of this force vector. So I'm going to extend that a little more on here. Okay, so this becomes the line of action. Okay, and then what am I saying? Okay, hey, if I'm trying to find the moment of this force about the point O, I can do the following. Okay, first thing is I'm going to take, and I'm going to call this point here, let's say that is the point A. Okay, so that's point A. I'm going to consider one more point on this line of action, which is the point B. Okay, and I'm going to take this figure once again and draw it in the next page, as you will see. Okay, so let me do that. These are all things that I'm going to be making use of again. Okay, so I'm going to bring that figure down here, and here is what you'll be seeing. Okay, I'm going to draw a position vector from point O to point A. Okay, so that's one thing that I have done. This is the position vector from point O to point A. Okay, then I have another position vector. I'm going to call this position vector as some R1 or R from O to A. Okay, then this is another position vector from point O to point B, which I'm going to call as R O B. Okay, and in order to recreate this entire idea, here is what I'm seeing. Okay, so I'm just recreating this, okay, by getting rid of some of this mess and so on. Okay, so I have this point O here. Okay, then I'm going to draw two position vectors from the point O all the way to the point A, where I call that as ROA, right? Position vector from point O to point A. Then I have another point which I'm saying, okay, it's point B. This is the point B. Okay, and then this is vector ROB. And then I have this force vector, as you can see from the previous figure, that is acting along these points. Okay, and the force vector is actually acting at the point A, but I'm just extending its line of action. So this is the force vector F, and this is the line of action. Okay, this is the point of interest. All right, so here is what I'm saying. Okay, I'm going to say moment about the point O due to the force F is going to be the position vector. Let's say I'm saying it's ROB cross to the force F. Okay, now here is what I can further say. Okay, from the triangle law of addition, okay, from the triangle law of addition, if I join the head of vector A and the head of vector B, okay, if I take that and if I align it directly this way, I get one more vector which I'm going to call as the vector R from the point B to the point A. Okay, and from the triangle law of addition, you know that vector R OB plus vector R BA is equal to vector ROA, which means that the vector ROB is vector ROA minus the vector RBA. Okay, then I'm going to substitute this. Okay, so substitute into the moment at F. Okay, this is by the definition. Okay, so if I do the substitutions, then moments about the point O due to the force F, which was R OB cross F, is now going to be ROA minus RBA cross F, which can be written as ROA cross F minus RBA cross F. Okay, I'm just using the distributive property of moments. Okay, but you got to think, by definition, so this is moment O about F. Okay, but by definition of cross product, if two vectors are coincident, their cross product is 0 because the angle between them is 0. Okay, if two vectors are coincident, then their cross product is 0. Okay, this is by the definition of cross product because the angle between them is 0. Okay, which means that if I go ahead and I look at the vector RBA and vector F, you will see that the vector RBA and vector F are coincident. Okay, so from our figure, okay, which is this particular figure that I just showed you now, RBA and F are coincident. Which tells me that RBA cross F is equal to the 0 vector. Okay, which tells me that, okay, if I started off, then moment about O due to the force F, if I started off as ROB cross F, this became ROA cross F minus RBA cross F, but then RBA times cross F is 0, which tells me that this is the same as ROA cross F, right? This is magically happening here. Okay, it's all taking place, which tells me that, for me, I can say that in general, moment about the point O due to any force F is some ROA cross F is equal to ROB cross F is equal to maybe some ROC cross F is equal to, and so on and so forth, where the point C could be some point here. I could choose a point C there, and then I could say, okay, take a position vector from point O to point C. Same principle that we have used here can be used. And so this is a fairly powerful statement that I want you to understand really well. Okay, this is very powerful. It's a powerful and a very useful principle. In a sense, it's called as the principle of the transmissibility of the moment. Okay, so the moral of the story is as follows. Okay, so in summary, moment of a force about a point is a vector. Moment of a force F is perpendicular to the plane containing the force vector and position vector. Okay, and the next thing is I can say, okay, moment of a force about a point is R cross F, which is also another R cross F, which is equal to another R cross F, and so on, where the position vector is from point of interest to any point on the line of action of the force. Okay, and very last thing, okay, so suppose the force F is some Fxi, Fyj, Fzk. Okay, and then let's say that ROA is some Xi, Yj, and Zk. Okay, I'm just supposing this to be the situation. Okay, then the moment of the force F about the point O, which is given as R OA cross F, can be given by the following determinant. Okay, this determinant, the first row of this determinant will have the unit vectors I, J, and K. The second row will have all the elements of the position vector, which is X, Y, and then Z. And then the third row will have the elements of the force Fx, Fy, Fz. And I'm assuming that we are all familiar with determinants, but when I solve a problem, I will of course go at least once very slowly using the determinants. Okay, so the first row of the determinants is the unit vectors. The second row will be the position vector. Okay, and then the third row will be the force vector. Okay, that's the second row, first row, and the third row, and I just want to point that out. Okay, so the first row is that, then I have the second row, which is this creature here. Okay, and then I have the third row, which is that creature there. Alright, so that is the basic summary. Moment is perpendicular to the plane containing the vector, position vector, and the force vector, so we can make use of cross product. Okay, so we can use cross product. Okay, and then when you do the cross product, it's always R cross F. Okay, it is never F cross R. And how do you choose the position vector R? It is from the point of interest, okay, to any point on the line of action of the force, which we just proved. And suppose if these are the force components, then how do I compute the actual moment vector itself? By making use of the idea of determinants. Okay, determinants, I hope I'll be going over some problems on these things, but I also feel that perhaps these are concepts that you have encountered in your prerequisites some time back. All right, all of you stay safe, and I'll see you in the next concept talk. Thank you.